YouTube homework 7. Um, this is the displacement of the block. This is the force on the block by the hand. So the direction of the force is parallel to the displacement. That is the definition of positive work. So by Newton's second law, constant force equal to constant acceleration. Therefore, the block is speeding up. Work is also equal to the change in kinetic energy. And as you can see, if the final velocity is greater than the initial velocity, then the work is going to be positive, which is described in this case. Number 2, so this is the displacement of the block. This is the force on the block by the hand. So negative work, meaning that the direction of the displacement and the force are anti-parallel to one another. So the block is slowing down because if work is negative, then the initial speed is greater than the final speed based on the work energy theorem. So work equal to 1/2 mv final square minus 1/2 mv initial square. So V final have to be less than V initial for work to be negative. So this is my free body diagram for each of the case, each of the following cases. So this is the block moving to the right. I have a normal force, gravitational force. There's the work of hand 1, and then there's a work of hand 2, and then this is the normal force, the gravitational force. This is the work of hand 1, the work of hand 2. So normal, gravitational, work of hand 1, work of hand 2. In this case, work of hand 2 is greater than work of hand 1. For the two cases, the work on hand 1 is greater. And then for the last case, so there's a normal force, there's a gravitational force, and the work of hand 1 is equal to the work of hand 2, the magnitude. So instead of a hand push with a force with the same magnitude, the Fnets as before are now at an angle below the horizontal. So the work would be less than the original work, assuming the force and the delta are constant. So explain how you use the definition of work to obtain your answer. So basically, if the angle of force point in the same direction at delta r, then the work is the greatest. So cosine of 0 degrees equal to 1. So based on this equation right here, so work equal to the net force multiplied by the displacement and then multiplied by the cosine of theta. So any angle beside 0 would give a cosine of theta less than 1. So the only way is to push directly horizontal, like parallel to the motion to get the most work. This is the force on the block by the hand. So for each force that you identify, state whether that force did positive, negative, or 0 work. So the normal and gravitational force does 0 work because they're perpendicular to delta r, which means their cosine of theta is 90, and that would be equal to 0. So the work of hand 1 does positive work, and the work of hand 2 does negative work. So this is what is stated in the problem. So the sum of the work done by all forces exerted on an object is called the net work. Is the net work done on the block in part A, B, positive, negative, or 0? So if the net force is parallel to the displacement, then the work is positive, which is, as you can see, cosine of 0 degrees is equal to 1. So if the net work is anti-parallel to the displacement, then the work is negative. So cosine of 180 degrees is negative 1. Is the net work done on the block greater than, less than, or equal to the work done by the net force? So the net work done is equal to the net force done on the block. The work done by each of the forces acting on the body is the same value as the work done by the net force, so they're equal. So generalize your answer in part A to D. Describe how the speed of an object changes. So if it has positive network, then it would be speeding up. Negative network meaning it's slowing down, and zero network meaning zero acceleration. So going with constant velocity. So my result is consistent with the energy work theorem. So the network equal to the final kinetic energy minus the initial kinetic energy. So if the block is slowing down, then the final kinetic energy is less than the initial kinetic energy and the work is negative. So if the final kinetic energy is equal to the initial kinetic energy, then the network equal to zero, which means that the speed doesn't change. So the work done would be twice that much for distance 2D, because d or delta r is proportional to work based on the equation work equal to force times delta r cosine theta. The speed of the 2D would be twice that much, because distance is proportional to velocity. So the kinetic energy of glider B is greater than that of A. So by the kinetic energy equation, 1/2 mv squared equal to the kinetic energy. The more masses something is, then the more energy you have to put in to make it move. So mass is proportional to the kinetic energy. So I solve for V up here, and then I plug V back down here. So I end up that with the 2m, I would get 2F delta R, and with the m, I would get F delta R. So the kinetic energy for 2m would be twice as much. So the work done on glider 1 by the hand is greater because assuming that delta R stays the same, the net force on glider A is greater because there's no pulling force opposed it. So an F net is proportional to the work done. So work equal to delta K equal to 1/2 mv final square minus 1/2 mv initial square. So glider A has more kinetic energy because the work done on glider A is greater. So it causes a bigger change in the kinetic energy. So the more work you put into something, the greater the delta K by the energy work there. When the block passes point R, is the spring compress or stretches. So you can tell with insufficient information. So yes, if the block is moving to the left, then the spring is being compressed. If it is moving to the right, then the spring is trying to decompress by pushing the block to the opposite side. So my answer for number 1 does depend on the direction of the block. So this is the direction of velocity at point R. Going to the left, this is the net force. This is the net force acting on point R, pointing to the left. And this is the direction of acceleration. There is a normal force, a gravitational force, and then a spring force to the left. So the network is positive because the displacement is in the same direction as the force, which means the cosine of theta is equal to 0. The theta is equal to 0, which give you a positive number. So again, this is the direction of the velocity at point L, and there isn't any force acting on it at point L, and There's also no acceleration as pointed out. There's only a normal force and a gravitational force. So the net work done is zero because the force is zero. At that instant, the block is not in contact with the spring, so there isn't any horizontal force acting on it anymore. So the speed of the block remains the same. So by the work energy theorem state that the net force causes an object to change its kinetic energy. In this case, the net work is equal to zero since the force is equal to zero. At the level of L, when the block is no longer in contact with the spring, it has some kinetic energy. If we ignore air drag and friction, its kinetic energy should still be the same on the right of point L. Uh, this is another proof for kinetic energy is conserved.